Okay, the unit circle and trig of any angles. I can understand how to find the sides of a missing right triangle. I'll explain why the right triangles are so important here in a little bit. I know that the sine and cosine and tangent of special right triangles, again, very important to know and remember. And I can find the trig ratio of any angle, even if it's not one of the special right triangle angles directly. So let's start this off by reviewing our special right triangle rules. For a 45, 45, 90 right triangle, you have an isosceles triangle, so those two are the same. That means that the hypotenuse is going to be that leg length times the square root of 2. So sometimes I may refer to as the leg times the square root of 2. So what that means is if x is 5, then this is x is 5, and the hypotenuse is 5 square root of 2. For a 30, 60, 90 right triangle, I have the short leg that is given to me. Then I know that the hypotenuse is 2 times that short leg, and you'll see me put SL a lot. The long leg here is equal to the short leg times the square root of 3. Okay, so for instance, if I know that this is 10, that's got to be 20, and that's 10 square root of 3. So those distances going to change. So here we go. There's the rules. I'd like you to find the distance of those missing sides. I kind of do it this way. I'm going to say, all right, well, there's my hypotenuse, so I'm going to set it equal to x equals the square root of 2. So I'm going to divide by the square root of 2. And to take 4 divided by the square root of 2 into simplest radical form, I'm going to multiply the top and the bottom by the square root of 2. Okay, that's going to reduce into 2 square roots of 2. Now, I don't have enough room here, but both legs would be that distance. Whereas here, if I got the short leg, that's awesome. That's perfect. I can just double that. So 2 times 6 gives me 12. There's a double in there, multiplying. And the long leg is going to be 6 times the square root of 3. Okay, we'll practice that a lot more. Now, the reason why it's so important is because we can use those to find the exact trig values. So I'm going to start off with 45. And I'll go with, say, this 45-degree angle. And that's just so I can say that this is the opposite side. This is the adjacent. And that's my hypotenuse. So sine is opposite over hypotenuse. I'll put a OA. So opposite over hypotenuse is 1 divided by the square root of 2. Well, with a little bit of manipulating, that turns into the square root of 2 over 2. The adjacent over the hypotenuse for cosine, so COA, is going to be 1 over the square root of 2. Well, it's basically the same thing. And that makes sense that the sine of 45 and the cosine of 45 are the same, because in a 45-45 right triangle, we have an isosceles right triangle. So now the tangent, I'll take 1 divided by 1, and I'll get 1. So I'm going to make my way back over to the other special right triangle and figure out 30s. So for 30, this is my opposite side, this is the adjacent, and this is my hypotenuse. So sine is opposite of adjacent, 1 over 2. Adjacent over hypotenuse, the square root of 3 over 2. And the tangent, which is going to be 1 over the square root of 3, or the square root of 3 over 3. Okay, now with 60, what's going to happen is this is just going to change spots. Now I'm looking at the 1 is my adjacent, and the square root of 3 is my opposite leg. So now the square root of 3 over 2 is my sine. Cosine is now 1 over 2, adjacent over hypotenuse. And now I have the square root of 3 over 1, which is just the square root of 3 over 1. All right, so get familiar with the two triangles, because this table here is very important. You're going to end up memorizing that to the point where you can tell me off the cuff of right off the top of your head that the square root of 2 over 2, hey, that's the sine of 45. That's a cosine of 45. Okay, because they're basically coming from special right triangles. All right. So now trig of any angle. Let theta be any angle in standard form. That means just that we have one side as the x-axis. xy is some other point somewhere out there. And r is the, well, basically it's the Pythagorean theorem, where x is one side of your triangle and y is the other side of your triangle. Okay? Sine is now y over r. And I'll explain that here in a little bit. Cosine of theta is x over r, so you just take the x coordinate over your radius. Tangent is y over x, except for when x can't be 0. You can't divide by 0. And cosecant is flipping sine. Secant rather is flipping cosine. Cotangent is flipping the fraction of tangent. Alright, so here we go. We've got the point -4, -3. So go over 1, 2, 3, 4, down -3. There's my point. Okay, we are going to put an angle such that it's the terminal side of theta when it's in standard form. So there's my theta. Okay, so really there's my one side, there's the second side, here's the 4, or -4, here's my -3. I'm going to use that to get my radius. Squared rather, and -3 squared. So that's 16 plus 9, 25, the square root of 25. The radius is 5. So the sine of theta is y over r. So -4 over 5. The cosine of theta is x over r. So -3 over 5. And the tangent of theta is going to be y over x, so -4 over -3, or positive 4/3. Okay, I don't know if I've really mentioned this, but my trick to remembering that sine and cosine are all mixed up because the one that starts with c, cosecant, goes with sine. Secant, the one that's S and C, see how they kind of match. You think the S's would go together, you think the C's would go together, but the Greeks couldn't get their business together and give you the right shortcut. And then the cotangent of theta is 3 over 4. Okay, so that's the trig of any angle. Make sure that you have the signs go with them, because in this third quadrant, quadrant number 3, sine and cosine will always be negative because x and y are both negative there. Tangent's the only one that's positive there because x and y are negative and tangent is a fraction of x and y. Okay, so what happens if your angle ends up being smack dab on the axis? Because see here, this -4 to -3 put me at an angle that's somewhere in the middle of the grid. It's not directly on. Well, if it's directly on, that means that your sine, cosine, and tangent kind of take the place of just your x and y quadrant. And what I mean is that your radius can change, but here is the point 1, 0. If I use a radius of 1, I just picked 1 for the heck of it. Sine is going to be y over r, so that's 0 over 1. That's going to work out to be 0. Cosine is going to work out to be 1 over 1 because x over r, 1. And then your tangent is going to be your y over x, so 0 over 1, 0. Okay, hey, just a second, wait. If that radius is 1, never mind, I'll point that out to you here in a little bit. Here I'm going to go with a radius of 2. That just means y's value is going to be 2. That's going to be at 0, 2. Okay, your sine is going to be y over r, so 2 over 2, 1. Cosine of 0 over 2, your x over r, 0. And your tangent of 2 over 0, undefined. Okay, and you can go through and do kind of the exact same thing here. Your r and y values kind of take those fractions with those radiuses. We'll practice this again a lot more, especially how this is going to work out. Now, this happened to have a radius of 5. We'll talk a lot about a unit circle later that has a circle with a radius of 1. Okay, so keep that in mind. But for sure, make sure you go back. You should be able to draw these two triangles, use them to find distances, and then use them to fill out this grid of 9 different values.